Dr. Ashe Matheny is an associate professor in the Department of Earth and Planetary Sciences at UT Austin. Her research focuses on understanding and simulating the ways vegetation influences the movement of water between the soil and the atmosphere. Ashley.
Howdy, y'all. I am going to start today's presentation with two caveats and an apology. The first caveat is if I seem a little loopier than usual, I have a newborn at home, and please take it easy on me. I haven't had more than 4 consecutive hours of sleep in a couple months now. My second caveat is that I am neither biologist or ecologist. I'm actually a hydraulics engineer, and so I'm a plumber of plants. Juniper being one of those plants, and this brings me to my apology, is that compared to many of my colleagues' presentations, I'm sorry I don't have as many pretty pictures, but I will try to do equally well at narrating what we do. Also, there are a couple of videos, and I'm not sure if they're gonna play. Could you give me a hand and click the play button for this one? So, my research group, similarly to what Pedro does, is we study the ecohydrology of landscapes. And we try to focus on the way that plants move water between the subsurface and the atmosphere. Thank you so much for that. So, when we think about this, a lot of times what we're thinking about is water moving through pipes, where pipes are the xylem vessels inside of the plants. And this movement of water is governed by supply and demand. So we've got our soil water or our rock moisture, like Pedro was telling you about, that's our supply function that's giving us the water. Maybe I can figure out how to do this today, sorry. That's giving us the water in our root zone. And we have our atmospheric demand for moisture that's actually the pulling force that's yanking the water out of the leaves of our plants. And so when we think about how this system is running, we're thinking about both the supply and demand balances, and what makes this fun to study, and the whole reason that my lab group does this, is because plants dynamically regulate this. Unlike plumbing and thinking about the plumbing of the city of Austin, that's just sort of a passive system, biology actively regulates the way that water moves. And so depending on what species of plant and what environment that plant is experiencing at any given time, so this varies based on season and this varies based on time of day, that we see different processes happening. And so when my research group and I study this, we do it at a variety of scales, and I'm going to talk about most of these scales today. So the first one is we make discrete leaf level measurements. So we measure how hydrated our leaves are, and we do that usually during time courses. So being up at 2 o'clock in the morning isn't really something that's new to me, just doing it not in the forest is. And we measure photosynthesis and how open our stomata, or those pores that let the water out of the leaf, are at any given moment. We also build sensors that tell us continuously how much water is being moved through that xylem, or how much water is being moved through those pipes at any given time, and how much water is actively there. And so for those of you who are wearing the Austin Fire, this is also a measurement of your live fuel moisture content. And so we're working on making this continuously available data to hopefully reduce some of the load on you guys. And then we compare that to micrometeorology, what we see above the landscape that tells us not just about the transpiration or the water flow within and from an individual tree, but also from the entire landscape put together. And based on the statistics of what sort of forest you have, what relative fraction of oak or juniper or pinyon pine that makes up your landscape, we can tell you how much of that transpiration comes from those trees, how much comes from your grasses, and how much comes from surface water sources. And so the data I want to share with you today is looking at across the Edwards Plateau, from Rock Springs, Texas, all the way out in Edwards County. Rock Springs is the county seat of Edwards County, if you haven't been there recently, to Dripping Springs, Texas. The difference between some ash juniper water use that struck me as really neat. So in Rock Springs, Texas, Rock Springs tends to be more arid than Dripping Springs. So Rock Springs is hotter and receives about 680 millimeters of precipitation each year, as compared to Dripping Springs, which receives about 900 millimeters. So our site out in Rock Springs has Juniperus ashei, lacy oak, and pinyon pine. It's a little higher elevation, and so those pinyon pine thrive out there. And in Dripping Springs, we've got our Juniperus ashei complemented with our Quercus fusiformis escarpment live oak. Now, Elizabeth asked me some questions about the two sites before I started this presentation, and so for her benefit and everybody else's, I want to share some of the similarities and differences. So we know the sites have different species compositions of trees. Now, for each site, there are at least 15 individuals of each species that are being continuously monitored. And so the data that I'm showing you, unless it's otherwise marked, is an average per that species. So you're not just looking at one individual tree, so it's not that one open air juniper standing by itself in the field. These trees haven't been clear cut in at least 50 years, so if we were to scroll back on Google Earth, we wouldn't see them being removed at any point in time. Their diameters are always more than 25 centimeters, so that's their DBH, their diameter at breast height. And we know for each site that there's about 10 centimeters of topsoil, followed by fractured limestone bedrock underneath. And that limestone bedrock is from two different formations of the two different sites. We've got the Edwards outcropping in Rock Springs, and we have the Glen Rose of the Dripping Springs site. So they're a little bit different, but the 10 centimeters of topsoil is the same between both. So before we go and look at what those trees are doing, I want to show you what a typical tree does so you can understand why our Texas trees are so cool. So if we look at mesic species, so these are species that I'm measuring in Michigan, and we think about what happens to a tree over the course of a day, and this is another video that may or may not play, so we'll see. Oh, there goes one animation. Can you click play on the blue tree on the side? So as trees respond to their microenvironment, what's happening as we go from dawn to dusk is that following the diurnal signal of insolation, so when the sun comes out, trees start to open their stomata to take in CO2 to photosynthesize, and as they do that, water leaves through that same opening. And so you see this upside down sort of asymmetric parabola around noon, where trees transpire really quickly in the morning after dawn, and then it sort of slowly tapers off, giving you that asymmetry that happens after the 12 o'clock hour. And so if you're looking at the computer simulation, what's happening over there is that our tree is starting fully hydrated. So think of it as a battery. You're totally charged and blue in the morning, so you've re-equilibrated to as much as you can with whatever your roots are experiencing, either in the soil or in the fractured rock. And as the day goes on, you start to lose water, and you lose water through the distal ends of your branches where your leaves are located, and that's why the ends of the branches become red first, and that sort of propagates inward as that tree stresses out throughout the day. And so if you think about that upside down parabola shape, what's happening there is that's when your plant is stressing out. So it's not able to pull the water back up through the xylem as quickly as it would like to in order to be able to photosynthesize with that sunlight. And you can think of that as wood's a pretty crappy straw. It takes a long time to move water through wood, especially if you're thinking about it in Texas, where our wood tends to be pretty dense as a protection from the arid conditions. So let's get back to Texas and let's talk about what our Texas trees do that makes them kind of weird. So this is for summers and springs, so spring being March, April, May, and summer being June, July, August, at our two different field sites. And so the Dripping Springs sites are represented by the solid lines, and the Rock Springs site is represented by the dotted lines, where the green lines are your juniper, and your yellow lines are the oak. So what's happening here, our Dripping Springs site, now remember this is the cooler one that receives more precipitation, those tend to form pretty typical parabolas that look a lot like Michigan. The Rock Springs site looks a little wonky, right? So when we're looking at this and it's looking a little wonky, if I were going to describe this to you, I would say that those trees out in the arid site are photosynthesizing in the early morning around 8 o'clock. Something happens around noon where they stress out. They're losing a little bit too much water. And then something else happens as the sun is going down. And so as an engineer who builds her own sensors, the first thought was, oh crap, we completely instrumented this wrong, something happened with the sensors. And so we went out and we checked, and we tried to make sure, did we do this right? And so what we found, once we took those sensors out of the center of the tree, and we put one down at the bottom and one up at the top, and we tried to see if they would give us different patterns. And we looked at what was going on with discrete measurements at individual time points in the leaves. What we saw was that the continuous data, the blue lines from the top and the bottom of the tree that are the solid and the dashed, they gave us the same signal. So it wasn't an individual sensor is going bad. And what we saw was when we did those individual leaf level measurements, and I'm going to draw a line through them so you can see the black dots a little better, is that they're showing us the same general pattern that we would expect, which is our tree is stressed out in the afternoon, and our tree is getting a little more hydrated at night. So we started to gain a little bit of confidence of, okay, it's not the sensors, it's not something that we've done wrong, we're seeing a phenomenon that's not typically talked about. And so we broke it apart and we looked more closely at this signal. And what we saw, and here I'm showing you some of the wood water content data. So if you're looking at the red line, that's the wood water content, where water content is high at night when it's not photosynthesizing, and it declines during the day as transpiration goes on. That's kind of what we'd expect. And if we look at it in the early spring, things look pretty happy, like that nice upside down parabola. But if we look at it in August, things start to get wonky. And notice that there's a factor of 10 difference on the y-axis on these plots, where in August we have 10 times less transpiration or sap flux going on. And so my lab group and I, of course, because we're UT Austin, we dubbed this the hook 'em horns, where we had a big spike in the morning and a big spike in the evening. And I'm sorry to my colleagues from A&M and Texas State. So as we parsed this out and we looked more and more at the data, what we saw was that the signal became really characteristic of as our site dried out. As we became more stressed out, we saw more and more of the hook 'em horns, where things got to be smaller and shifted towards earlier in the day when humidity is higher and temperature is lower, and late in the day when the same conditions exist. So our trees are basically capitalizing on the least stressful time of day to transpire. Now, interestingly, this pattern not only existed in our ash juniper, but it persisted in all of our species of the arid site. So the pinyon pine, the lacy oak, and the ash juniper all do this. And it was consistent between observational years. So we instrumented this site continuously from 2018 to 2021, at which point one of my master's students graduated and we decided, to heck with Rock Springs, we'll move the instrumentation to Jamaica. He wasn't very happy about that one. So when we were looking at this, we were thinking, okay, we have something here. And we looked closer at that supply and demand of what was causing this stress. Was it just that we're not able to get enough moisture through the roots? Or was it that there's something different in the atmosphere? And so the first thing we looked at was atmospheric demand. So vapor pressure deficit is, you can think of it kind of like the opposite of humidity. It's a measure of how dry the atmosphere is or how much pulling force is yanking the water out of the leaves. And so when we looked at the 3 species in the Rock Springs site, we found that all of the species have their water withdrawal, so how much water is being sucked out of that xylem every day, is strongly and significantly correlated to how much atmospheric demand for vapor pressure there is. And the same thing for soil moisture, is that we saw that we were also being governed by soil water content. So it's not just a case of we're seeing stressed out trees because we don't have enough moisture in the ground, but it's also we see stressed out trees because we don't have enough moisture in the atmosphere. And for my fire colleagues, you guys know this because fire weather is often indicated by high vapor pressure deficit. In fact, many of the last wildfires that we've seen that have been extreme have been characterized by extreme vapor pressure deficit antecedent conditions before the ignition of that fire. So to go back and talk a little bit more about what the title of the talk promised that I would talk about, which was juniper clearing, our property owner out at Rock Springs, she had read that clearing the juniper off your property will create more stream flow. Now, if you've been paying attention to the species-specific plots that I've been showing, our juniper clearly don't use any more water than any other tree. But she wanted to do it anyway, and her hypothesis was that at the base of her hill slope, where there was a little spring, that she would see increased stream flow. So she cleared off 30 acres of juniper. Mechanical clearing just pushed them down and waited for them to die. And it happened in 2019. And we continued to monitor the site for 2 years afterwards. So what we found was that transpiration did increase after clearing the juniper. What we did not find was increases in stream flow. So the trees that were immediately adjacent to the clearing, those were the trees that increased their transpiration, because they immediately had access to lower competition and not necessarily this increased moisture coming from the ground. So it wasn't exactly what she expected at all to happen. And if you were to look at the trees that were immediately adjacent to that spring, they registered no change in transpiration from year to year based on that clearing. So it didn't propagate any further than a few kilometers away. So what does this mean for Texas's future? I've got my 1 minute left, Mark. So if you're thinking about the future of Texas, one of the things that we talk about with respect to climate a lot is the 100th meridian, which historically has been right there through the center of Texas, and the Dripping Springs and Rock Springs site bracket the 100th meridian. So this has been historically the division between the arid west and the humid east. And so as we track future climate conditions, it's expected that our 100th meridian will move to the east. And as that moves eastwards, we can expect our trees that are in areas like Austin and Dripping Springs to experience more similar climatic conditions to those that are experienced in Rock Springs. So what does that mean for us? Well, that means we can expect higher vapor pressure deficit or atmospheric demand, so more fire weather, lower soil moisture, which means we can expect drier vegetation, so less live fuel moisture content, but also that we can expect less carbon uptake for photosynthesis, which means higher atmospheric CO2. And if we think about transpiration as a cooling process, because it takes energy from the atmosphere to evaporate that water, we increase air temperatures because that energy has to go someplace else. So we see lots of interesting feedbacks and phenomena that we'll continue to experience as we look towards the future. So I will shut up and let you guys get on to your break now with a huge thank you to my research group and graduate students, without whom this would not be possible. Absolutely. So if you think about the tree and you think about the pretty rainbow graph that was going in and out with the red and blue, so typically pre-dawn, so 4 or 5 a.m., your tree is the most hydrated that it will ever be for that day. And so it's had all night of not opening its stomata to photosynthesize, because why open your stomata if there's no sunlight for photosynthesis? And so as it's recharged early in the morning, that's the wettest it'll ever be. And then as the day continues to go on and you get closer and closer to solar noon, you'll get into that period of extreme stress where it'll be the driest it will ever be for that day. So time of day absolutely matters. So in this study, so this is a study from the Lamont Doherty Earth Observatory at Columbia University. And what they were tracking was they were tracking CMIP-6. So CMIP is a coupled model intercomparison project, which to you guys probably doesn't mean much at all. But what it means is they took the 25 best models for simulating land-atmosphere interactions and that are the most reliably good at predicting what Earth's weather and climate will be. And they compared thousands of runs of each of those 25 models, and they assessed what the percent change would be in precipitation, in soil moisture, in temperature, and in humidity. And they looked at historically where the dividing line, so the 100th meridian, the name of it refers to the longitude of where it would be. Latitude, longitude. I'm sorry, I'm sleep deprived. So in this case, what we're referring to is simply the dividing line between the arid west and the humid east. And so as they were looking at those temperature and humidity and precipitation conditions, basically what they said was this dividing line that marks the distinction between arid and humid across the United States will start to shift to the east, meaning that areas that fall right along the Great Plains up here, where we have lots of our farmlands, are going to become more arid in the immediate future, where we will have less precipitation, which will generate lower soil moisture and higher evaporative demand. And so as we think about the way our climate will shift, we're starting to think about recategorizing these areas. Does that make more sense? find me on the break and I'll try to explain it a little better. So, of course, with all models, this has a huge margin of uncertainty on it because there are lots of uncertainties. These are taking into account carbon emissions, methane emissions, different use strategies, different emissions cutback strategies for all of these different scenarios. And so this could be 50, 100, 150 years in the future. I have, but haven't had a good opportunity. So our 2 field sites that we used in this study came to us opportunistically. So the Rock Springs field site, the property owner was very interested in having some actual data of what would happen during and after the clearing. And the Dripping Springs field site is a new permanent field location that was actually donated to the University of Texas. And so while that one will be a long-term study, not long enough to make it an old growth site. So if you've got sites that you would like instrumented, let me know and I will happily come stick sensors in your trees. And I have a great record of not killing the trees. That's the important part about wanting continuous data.